Swayam Prabha. Digital India. Educated India.
Welcome back to lecture number 25, part 2. I will be solving one more design problem in the lecture number 25, part 2. Already we designed one cold storage for a negative temperature application, that is in the part 1 of this lecture. In addition to that one design, I am going to design another problem. So let us quickly move to that one. So this is already discussed in the previous lecture itself. Like there are four components like due to when we consider the pre-cooling, that is Q1 MCP from T1 to T2, then from T2 to TF, that is sensible heat above freezing, TF at freezing point, that is a latent heat, then from TF to T3, that is sensible heat below freezing. So because of that, there are four heat quantities Q1, Q2, Q3 and Q4, where T1 is the initial temperature of the product, T2 is the temperature of the product after pre-cooling, and T3 is the final temperature of the product. So now we are going to design a cold storage for freezing fish in a plate type of freezer. So there is one difference between the previous question under this lecture number 25, part 1, and the second design problem. In the previous one, I have designed a blast type of freezer for cold storage, negative temperature application. And in this problem, we are going to see how to design a plate type of freezer for a negative temperature application based on the conditions given. Ambient condition is given 40 degrees centigrade. The product loading temperature in the plate freezer is given as 15. Quantity to be frozen per batch, that is 1 ton, 1000 kg. Product temperature below freezing is given. So this is the product loading temperature. Specific heat capacity above freezing is given. Freezing temperature is given. Latent heat of freezing, specific heat capacity above freezing. This one it is given. The difference between the previous design and this design is the previous one is for batch type of freezer, and this one we have to design the cold storage for a plate type of freezer. Let me emphasize that in the blast type of freezer, the cold air is circulated with a high velocity to achieve the cooling at a rapid rate. And in case of plate type of freezer, cold or chilled plates are used which are in direct contact with the product for cooling the product. So let us, if we see the specific heat capacity value of this, the design problem number 2 and with the previous one, it is same 3.78 and 2.14. Product storage temperature is 15, freezing point is minus 2.2, and that is the product temperature below freezing is minus 20. Question number 2. So product to be stored is fish. CP value is equal to 3.78 kilojoule per kg Kelvin. This is above freezing. CP value is equal to 2.14 kilojoule per kg Kelvin. This is below freezing. Temperatures are given. T2 is equal to 15 degrees centigrade. Freezing temperature is minus 2.2. The data is same. Only thing is we are designing for a plate type of freezer instead of a blast freezer. And T3 is, I think it is 10 degrees centigrade, minus 10, minus 20. So it is minus 20. Product temperature below freezing is minus 20. Minus 20 degree centigrade. Latent heat is given as 253 kilojoule per kg. In the question it is given as, the latent heat is given as 253 kilojoules per kg. 253 kilojoule per kg. 253 kilojoules per kg. So this, the plate freezer, in this there is no, the dimensions are not given, so it is, the transmission load is not calculated, is not there. There is no infiltration load in a plate type freezer. There is no infiltration, lighting or occupancy load, and only the product load is to be considered. Because here the cooling is achieved by using a cold plate, which is in direct contact with the product. So there is no lighting load, there is no occupancy load, there is no infiltration load. Minus 20. So let us calculate the product load. So sensible heat above freezing. So here also, since the pre-cooling conditions details are not given, so Q1 is negligible. I will be calculating Q2, Q3 and Q4. Of course, Q5 is a respiration load which is not applicable for a dead product. So sensible heat above freezing is, that is cooling from this temperatures, 15 to minus 10. Cooling from 15 degrees centigrade to minus 2.2 degrees centigrade. The quantity is given as 1 ton, I think. It's 1 ton because the data are almost similar to the previous problem. Mass is given as 1 ton. M equal to, so that M is equal to 1 ton, which is equal to 1000 kg. So this is Q2 is equal to MCP from T2 to TF. T2 to TF. So M is equal to 1000. CP is, this is above freezing. So we have to put this value of CP, 3.78. So let me substitute again. 3.78. T2 is 15 minus the freezing temperature is minus 2.2. We get Q2 is equal to 18,65016 kilojoule. 5016 kilojoule. That is equal to 65016 divided by 3600. We will get it in, this is in kilojoules per second. So Q2 is 18.1 kilowatt. 18.1 kilowatt. The sensible heat load is Q3. So this is the calculated sensible heat above freezing, that is cooling from the temperature of 15 degrees centigrade to up to freezing temperature. Next one is latent heat. Latent heat, that is Q3 is equal to M into H of latent heat. M is 1000. Latent heat is given in the problem, 273 kilojoule per kg. 273. So that is equal to 273,000 mass in kilogram, this is kilojoule per kg, kg and kg will get cancelled. So we will get the unit in kilojoule. So this is equal to 273 divided by 3600 kilojoules per second. So Q3 is equal to 70.3 kilowatts. 70.3 kilowatts. Next one is sensible heat below freezing. That is Q4. That is equal to MCP into TF minus T3. So this is cooling from freezing temperature minus 2.2 degrees centigrade to minus 20 degree centigrade. This is above freezing, that is from 15 to minus 2.2. Then from minus 2.2 to minus 20, this is below freezing. So here the CP value should be substituted for below freezing C. This value to be substituted, 2.14 into TF is minus 2.2 minus of minus 20. So when we calculate, Q4 is equal to, this is Q4. Let me write it clearly. This is Q4. So Q4 is equal to 38092 kilojoules. 38092 kilojoules. So that is equal to 38092 divided by 3600. When you divide by 3, we will get it in kilojoules per second, which is equal to 10.6 kilowatts. 10.6 kilowatts. Now let me write it here also. Respiration load Q5 is equal to 0 since fish is not a live product. Frozen fish is not a live product. Therefore, the product load is equal to product load QP is equal to Q1 plus Q2 plus Q3 plus Q4 plus Q5. So Q1 is negligible, that is 0. Q2 we have calculated 18.1 plus Q3 is 70.3 plus Q4 is 10.6 plus Q5 is 0. So when we add, the total product load comes to, so Q1 plus Q2 plus Q3 plus Q4 plus Q5, when you add, you will get 99 kilowatts. This is the calculation, 99 kilowatts. 99 kilowatts. Next, the second load is equipment load. That is QF. The fan details are given. Number of fans are 2 of each 1.1 kilowatt. So from table 2.12, this is 1.1 kilowatt. This is motor kilowatt. And the values to be referred. This is the connected load in refrigerator space. It comes to 1453 watts. From ISHRE handbook, ISHRE cold storage design guidebook, table 2.12, corresponding to 1.1 kilowatt. The connected load in refrigerated space is 1453 watts. That is the value which I have taken from, which is from the table, from this table 1453. So now we can calculate the equipment load. QF equal to number of fans multiplied by the connected load in refrigerated space. Let me write it. GRA, refrigerated space. So number of fans is, I think it is 2. 2 into 1453, which is 2.9 kilowatt. 2 into 1453 is equal to 2.9 kilowatt. So now the total load is, already it is, I have explained that in a plate type freezer there is no lighting load, no occupancy load, there is no infiltration load. Therefore, in a plate freezer, infiltration load is equal to 0, occupancy load is equal to 0, and QL is equal to 0. So therefore, total load is equal to product load plus equipment load. So product load is 99 kilowatts. Equipment load is 2.9 kilowatts. So the total load is 101.9 kilowatt. That's what I have calculated. 101.9 kilowatt. Not 1.9 kilowatt. So here transmission load is also not there. So QT is also 0. So out of the 6 loads, only 2 loads are there. One is product load, another one is the equipment load. Considering the safety factor of 10%, Q is equal to 101.9 into 1.1. So that is Q is equal to, so this is 101.9. So it comes to 112.1 kilowatt. 112.1 kilowatt. Now, for a compressor running time of 18 hours per day, which is given in the question, for a compressor running time of 18 hours per day, for a compressor running time of 18 hours per day, the total refrigeration load is equal to equal to 1112.1 into 24 by 18. It comes to close to 150 kilowatts, 149.5 kilowatt. So if you look at this problem, so here, though I have calculated the total load, it will be the summation of Q is equal to total load Q is equal to transmission load. Let me write it in the next line. Q is equal to transmission load plus product load plus infiltration load plus equipment load plus occupancy load plus lighting load. So these things are 0. This is not there. this is not there, this is not there, and this is not there. So only we have the product load, and that's why I have added these two. So this is about the complete design of, this is the design of cold storage using a plate type of freezer for a negative temperature application. Whereas the previous problem, it is based on designing a cold room using a blast type of freezer, a blast type of freezer. Even in the blast type of freezers, I mean, not all the loads are calculated. According to the data given, some loads, whatever the data given, the conditions for designing the cold room, the loads have been calculated. But similar to the plate type of freezer, not all the loads are applicable for a blast type of freezer. So let me conclude this lecture with this. Thank you.